Welcome to the mean value theorem. We're actually going to spend more time today talking about consequences of the mean value theorem than we are the theorem itself. But I want to present to you two theorems that we use a lot in mathematics, and I'll have you just read through them, but I'm going to explain them with pictures. So the intermediate value theorem says that if you have a continuous function on a closed interval, so over here, I've got a picture of a continuous function on a closed interval from A to B, and f of A is probably around here, and f of B is probably about here. The theorem says that if you take any number m in between f of A and f of B, then there's a number c between A and B such that f of c is equal to m. So in my picture, I need to lower m a bit right there. All right. And then the mean value theorem says, again, you have a continuous function on a closed interval, but it's also differentiable. It says that there's a number c between A and B where the slope of the tangent line, that would be f prime of c, is equal to the slope of the secant line that you see here between A, f of A, and B, f of B. The slope of that secant line is right here, and that's equal to f prime of c. All right, so now let's talk about some consequences. Number one is increasing, decreasing. So you don't have to memorize this. I just want you to know what increasing is, and it's very simple. As you move from left to right, a function's increasing if it's going up, and it's decreasing as you move from left to right if it goes down. Very simple, but we have a test for that using derivatives, and this is it. If the first derivative is positive, then you've got an increasing function, and my notation for increasing is this up arrow. It's not universal though, it's just shorthand that I use. If the first derivative is negative, then f is decreasing, and if it's identically equal to 0, then f is constant. Now, functions can only change between increasing and decreasing at certain places, and these are those places. They can change at critical numbers. So right here, we've got a critical number. The function's going down, and then it's going up. Again, right here, a function's going up, and then it's going down, and where it changes, there's a critical number. F prime does not exist there. You've got a corner. And over here, f prime is 0 because you've got a horizontal tangent. And what we see in this last picture is a place where a function goes from decreasing to increasing at a point not in the domain because there's a vertical asymptote there. So a quick way to figure out where a function's increasing and decreasing is to make an f prime number line. And what you do is you just make a number line and you plot the critical numbers and the numbers not in the domain. And then you're going to test the sign of f prime on the intervals that are formed from plotting those numbers. By the way, there should be no other numbers on your number line. So when we use test points, we're not going to put those on our number line. And I'll tell you what I mean by that in a sec. All right, so here we've got a function. We want to find the critical numbers and make an f prime number line. And just to remind you, the definition of a critical number, it's a number that has to be in the domain, and it's a place where f prime is equal to 0 or it doesn't exist. So let's start by finding the domain. This is a polynomial, so the domain is all x. All right, now let's find f prime. F prime of x is equal to 3x squared minus 6x. And we need to factor that. Let's pull out a 3x, and then we're left with x minus 2. So now we know f prime of x equals 0 at x equal 0 and 2. So those are our critical numbers. There are no places where f prime does not exist. So that's a never. All right, so now we're ready to make a number line. Here it is. I always like to label my number lines because pretty soon we're going to be doing f double prime number lines. So f prime, and I put the factored form of f prime, plot 0 and 2. And now we just need to determine the sign of f prime on those 3 intervals that I've formed. So when I test this first interval, I'm going to test x equal -1, and f prime, I'm not going to actually evaluate f prime of -1. What I'm going to do is I'm going to look at these 2 factors, 1 factor, 2 factor. I'll determine whether they're positive or negative, and then I'll multiply. So when x is -1, the first factor is negative, 3x is negative, and the second factor is negative. 2 negatives is a positive. So my function's increasing there. When x is 1, that would test the middle interval. F prime would be a positive factor times a negative factor. So that's going to be a negative. And finally, when x is 3 maybe, f prime will be a positive factor times a positive factor, so positive. So f is increasing on negative infinity to 0, union 2 to infinity, and it's decreasing on the middle interval from 0 to 2. Okay, let's do a slightly more difficult one. We're going to find the domain and critical numbers, and we're going to write f prime as a single fraction without negative exponents. So that's the important part, and you're going to have to get very used to doing that. So the domain is all x. There are no negative exponents, there are no even roots, and there are no logarithms. So now we can find f prime. That's 2 equals 2 minus 2x to the negative 1/3. And I want to write that as a single fraction. So that's 2 over 1 minus 2 over x to the 1/3. So my common denominator is x to the 1/3. So I multiply 2 by x to the 1/3 over x to the 1/3. And that gives me 2x to the 1/3 over x to the 1/3 minus 2 over x to the 1/3. And that's equal to 2x to the 1/3 minus 2 all over x to the 1/3. And we can factor that a little bit further. Take the 2 out, x to the 1/3 minus 1 over x to the 1/3. Okay, perfect. Now f prime of x is 0 when the numerator is 0. If we look at this numerator, it's 0 when x is 1. And f prime of x does not exist at the places where the denominator is 0, and that's x equals 0. Those are both in the domain, so they're both critical numbers. So those are the numbers I have to plot on my number line. So here's 0, here's 1, and I'm testing 2 times x to the 1/3 minus 1 over x to the 1/3, and that's f prime. So there are two factors. Well, there are actually 3 factors, but 2 is always positive, so we're going to ignore it and just look at the factor on the top in parentheses and the factor on the bottom. So for the first interval, from negative infinity to 0, I would test x equal negative 1, and then f prime will be on top when x is negative 1. The cube root of a negative number is still negative, so the top's going to be negative, and the bottom is negative, so I'm going to have a positive there. Now a number between 0 and 1. Well, you might think, well, I'm just going to pick a half, but I'm going to pick something where we can actually look at the sign of f prime more carefully. I'm going to pick an 1/8, and then f prime, when I look at that, I know that the cube root of 1/8 is a half, so I can see that the top is going to be negative, and the bottom is positive. So this is going to be a negative. Pause if you have to work that out. And then x equal, for the last interval, I'm going to go x equal 8 for the same reason. Then when I do f prime, on top, cube root of 8 is 2. 2 minus 1 is a positive number. And on the bottom, 2 is positive, so this is positive over positive, so I've got a positive. Okay, and that's all we had to do for this problem, but if you were asked the increasing and decreasing intervals, the increasing ones have a plus on them and the decreasing ones have a minus on them. Okay, and that is the end of this section.